Okay, this section is going to be problems 32 through 43, problems 32 to 43, actually 31 to 43. And we're going to start with problem number 32. When making an inference about a population mean, which of the following suggests the use of a z-score rather than a t-score? Super important concept. I'm so glad this got asked. All right. The variance of the population is known. So if we know the standard deviation of the population, this is a z. If we have to use the standard deviation of the sample, it's a t. So this could be also the variance. So if we're using the variance of the sample, it's a t. If we're using the variance of the population, it's a z. So the variance of the population is known. That tells me I get to use a z, because that's the saying that I know that value. Okay, so that's number 32. In a one-sided hypothesis test, this is number 34, in a one-sided hypothesis test for the mean for a random sample of size 15, the t-score of the sample mean is 2.615. Is this significant at the 5% level, at the 1% level? This is a great question. This is one that stumps people because they forget about a part of the calculator. Okay, so this is a t distribution. T is also set on 0. And so the mean is 0. And we ended up with a test statistic or an X bar or test statistic of 2.615. And we want to know the probability that it goes up. Our natural inclination is like, oh, we see T and we naturally want to go stat test, T test. And so you're all right, okay, my mean, 0, X bar, 2.615. And then I see I don't have a standard deviation, and so I feel stuck. It's because we're in the wrong part of the calculator, and we have to go second vars. TCDF, lower bound, 2.615, upper bound, infinity, degrees of freedom. Be careful, we have a sample size 15, so my degrees of freedom are actually 14, or 15 minus 1. But when I end up with that, I end up with a 0.01. And if I compare that to alpha, that's less than an alpha of 0.05. So I'm rejecting at the 0.05 level. So this is a reject. I really should write 0.0101, because that's what it is. Then I have a 0.0101, and I'm comparing to a 0.01, and this is greater than. So I'm rejecting at an alpha level of 0.05, but I failed to reject at 0.01. Significant at the 5% level, but not at the 1% level. So this is that one. All right, this is a great question. This is question number 36. And in this question, the 6.779 annual boat race between Oxford and Cambridge is watched by an estimated 250,000 fans from the banks of the river. The average weight of these cruise members has been around 180, but a U.S. sports statistician believes that the average weight of all collegiate crew athletes is less than this. In a random sample of 50 U.S. crew members, a hypothesis test mean is 180. Alternative is less, results in a p-value of 0.078. Okay? Using the data among the following, which is the largest level of confidence for a two-sided confidence interval that does not contain 180? So, we currently have a p-value of 0.078 for a less than. But we want to convert this to a hypothesis test, which is a not equal to. This is key. One tail to two tail, double. So double your p-value. So that means I'm going to have a 0.078 here and a 0.078 here, and I need to find out what's left in the middle. So what's left in the middle is this, 1 minus 0.078 times 2, 0.844. So what is the largest level of confidence for a two-sided confidence interval that does not contain 180? That. Because when you go from one tail to two tail, you have to double. One tail to two tail, you double. Once again, one tail to two tail, you double your p-value. So 0.078 times 0.078 gives, 0.078 times 2 is 0.156. So that's my area in the tails, and the rest of my area ends up being 0.844. So 84% would be my best answer. Now, real quickly, if we go from two tail to one tail, we either half or 1 minus the half. Two tail to one tail, half or 1 minus the half for the p-value. From one tail to two tail, you double. This is an always. From one tail to two tail, you always double. Suppose fastball speeds in collegiate baseball are normally distributed with a mean of 80, this is number 38, with a mean of 86 and a standard deviation of 4. Suppose further that the major league scouts will only consider pitching prospects who can throw a fastball at least 90. What percentage of pitching prospects who are considered can throw over 95? So this is given that they can throw, given greater than 90, what's the probability of greater than 95? Well, that's kind of a lot of work, and it is. So first off, let's draw a picture of what this looks like. They say college is throwing in an 86. And we want to know the probability of 90 or greater, because we got to find our denominator first. So the denominator is going to be the probability that x is greater than 90. So that's the probability that z is greater than 90 minus 86 over 4. That's the probability of the individual. And I can go about this several different ways, but I'm going to do it with a normal CDF, second vars, normal CDF, lower bound is 90, upper bound is infinity. Mean of 86, standard deviation of 4. So that denominator happens to be 0.1586. That's what we just calculated. That's how many of them throw faster than 90. But the numerator is going to be the probability that z is greater than 95 minus 86 over 4. So second vars, normal, CDF. And I need to change my lower bound to 95. And do the same thing. And I get 0.0122. So this 0.0122 divided by the previous is 0.077. So about 7.7% of those who can throw faster than 90 can actually throw faster than 95. So about 7.7% of those who can throw faster than 90 can also throw faster than 95. All right, so number 40, car insurance policies for teenagers have higher premiums. This is for adult drivers because teenagers are considered to be at a higher risk. Suppose the average yearly cost of teenagers aged 16 to 19 is $3,025 with a standard deviation of 430. Is there sufficient information to answer either or both of the question? So what is the probability that a randomly chosen teenage driver pays over $3,000 for insurance? I cannot do this problem. Why? An average teenager is just one, and I do not know the distribution. If I knew the distribution was normal, I could do this. But since I don't know what the distribution is, I cannot do number one. So I cannot perform number one. What is the probability average amount paid in a simple randomness sample of 50? Well, this is going to be normal by central limit theorem. So that's going to be normal by central limit theorem. So I can do number two. For this one, I would have to know that the distribution was normal. I don't, so I can't do it. This one, because the sample size is 50 or larger, I can do it. So I have sufficient information to answer question 2, but not sufficient information to answer question 1. All right? All right, this is question 41. In a random sample of 50 mathematics majors at a large state university, their mean GPA on a 4-point scale was 3.65 with a standard deviation of 0.25. Which of the following is most likely true about the distribution of GPAs among math majors at this university? Well, since I know a little bit about this problem, it's been a while since I've done it. Let's take a look at things real quickly. Let's go ahead and try and draw. I'm going to try to draw this out. I don't know if I can. I'm going to try to make a big normal curve. And it happens to be centered at 3.65. Okay, so if I have a standard deviation of 0.25, 1, 2, 3, so normal curve, I should have 3 standard deviations going up. I should also have 3 standard deviations going down. So this way, this would be 3.4, 3.15, and this would be 2.90 if I subtracted correctly. 2.90. Going up, I add 0.25. This becomes 3.9. This becomes 4.15. This becomes 4.40. You can't have higher than a 4.0, so this is going to have to cut off right here at about 4. So this part does not exist because you cannot have an average of 4.0. So what is that value? 4 minus 3.65 divided by 2.5, because that's my z equals x minus mu over sigma. And I end up getting, since the maximum possible GPA of 4.0 would have a z-score 1.4, the distribution is skewed to the right. And we can look at this and go, you know what? Yeah, you're missing those values. So it's going to be, excuse me, not skewed to the right. I said that wrong. It's skewed to the left. It's stretched to the left. So that needs to be skewed to the left, or letter C, because it's been pulled this way. In fact, we can also expect that there's probably GPAs less than 2.9. But nonetheless, we know it can't be normal because we don't have any, we can't go above a 4.0. Researcher, this is number 43, research has shown that tornado wind speeds are normally distributed with a mean of 112. Consider random samples of 10 tornadoes each. All right. So we have an S. All right. The fact that this is an S means it's not a normal distribution. So it has a T distribution. Degrees of freedom is 10 minus 1, which is 9. So that's letter B. All right. Now, had this been if this had been that, then it would have been a normal. But since it's an S, the distribution is a sample, it's going to be a T distribution. We haven't studied chi-squared yet, and it doesn't apply anyway, but we try not to give you questions that you haven't seen before, or try not to give you things that we haven't talked about before.